So we're getting close to the end of the quarter. Now, we need to see what we talked about last time. So last time we talked about indefinite integrals. And we only really have a handful of them. And remember, you will have all these formulas given to you, so you don't even have to remember them if you don't want to. But if you plan to go on in calculus, you should know these. These are important. The integral of x to the power a dx, well, you add 1 to the power, so you get x to a plus 1, and you divide by that new power. So 1 over a plus 1, x to a plus 1, and of course you always add a constant. And this works as long as a is not negative 1. On a side note here, just let me mention on the final, you might see a problem where we ask you to do an integral. Obviously, it won't be this one. It'll be something more interesting. Don't forget your notation. Notation is very important. For instance, if you leave off a plus c, you'll lose points. Maybe 1, maybe 2, but you'll definitely lose a point, at least. So remember notation. Notation is very important because these constants do come into play, especially when you have things like initial value problems when you go on to differential equations. So constants are important. So don't forget those. The indefinite integral of sine, or if you like, we could just say the antiderivative, because antiderivative and indefinite integral are really the same thing. So indefinite integral or antiderivative of sine is negative cosine. Indefinite integral of cosine is sine. Indefinite integral of secant squared is tangent. Indefinite integral of secant tangent is secant. And the indefinite integral of 1 over 1 plus x squared is arctangent. And of course, I left off my plus c. Okay, I'll tell you right now, there is going to be another arctangent problem. So don't be surprised. You'll see them in the practice midterms too. So arctangent is our bonus. You know, most 31A classes, they don't get the arctangent. So you're special. You got the bonus because you got me. Now, last time we talked about definite integrals. Now, definite integrals are a little bit different than indefinite integrals. Well, first off, the indefinite integrals has this in. But indefinite integrals, really, you start with a function and you end up with another function. Definite integrals, you start with a function and you're going to get a number. So these definite integrals measure something. And the difference notationally between a definite integral and an indefinite integral are these a's and b's. So last time, for instance, we saw that if I have a function f of x and it's less than or equal to g of x, and of course, if f is smaller than g, then the integral of f is smaller than the integral of g. Of course, I did the really stupid mistake where I drew the picture and I got them backwards. So I had to write f and g, but of course, that's the wrong picture. I should have written g and f. G is the larger function, so g goes on top. I'm sorry. Mea culpa. My apologies. So this is the right picture of last time, so just get out the whiteout and correct your lecture notes. Where's my eraser? There it is. Which, of course, I mean, I said f is smaller than g, so I should have had the right picture. So I apologize. And from this simple fact, we have the following. Suppose f is bounded between two values, small m and large m. Well, in that case, on this interval a to b, in that case, you can say that the integral from a to b of f divided by the length of the interval, which is b minus a, is in between little m and capital M. We'll get back to this later. Intuitively, what you can think of, we'll talk about this in a few lectures. This is the average value. And it acts something like the average rate of change. And in fact, we'll talk about a mean value theorem for integrals, just like we had a mean value theorem for derivatives. And we'll use this today. But the important thing we talked about last time was the fundamental theorem of calculus, part 1. Now, let me just tell you that we call it the fundamental theorem of calculus, part 1. And today, we'll see the sequel, the fundamental theorem of calculus, part 2. Of course, sequels never are as good as the original. Titanic 2 just flopped at the box office. No one wanted to see it. But it depends on what book you have, which one is called 1, which one is called 2. So our book calls this 1. Some books call this 2. It doesn't really matter. They're both basically saying there's a relationship between derivatives and antiderivatives. And this one says, if you have a continuous function on the interval a to b, say this function is the little f of x, and capital F of x is any antiderivative of little f of x. Doesn't matter which one. Now remember that antiderivatives are not unique, because you can add constants. So if I have one antiderivative, I can add 5, I can add 7, whatever. So the moral is I just start with any, so usually we just choose the one where the constant is 0 or something simple. Okay, so I have an antiderivative of little f of x. Then the way to evaluate the definite integral from a to b of little f of x dx is to just evaluate the antiderivative at b minus the antiderivative at a, which another way to write this notationally is f of x. This line here, this bar, means you're doing some evaluation. In this case, evaluate b, and then subtract, evaluate a. So these two mean the exact same thing. So you'll see both in the book. So now we have a new way to do definite integrals. Remember what we did before with definite integrals. The idea was, well, we're going to take what we want to find. Let's think of it as some kind of an area. And we chop it up into tiny little pieces. And then we add all the little pieces up, and that gives us a good approximation. How do we get a better approximation? Oh, chop it up into smaller pieces. And we say, OK, that's better. How do we do even better? And we say, oh, OK, even more pieces. And we just keep going forever and ever and ever until eventually we say, OK, we can see what's happening. There's some limiting process. We can see what the value is. And it was like, oh, OK, that took a long time to do very simple functions. This says, oh, just skip all that. You don't need it. If you understand what the antiderivative is, it's very easy to do. Much faster, much more simple. And because we have this far superior technique to doing Riemann sums, and Riemann sums are cool, don't get me wrong, I think this is more important. So I'll tell you right now, I'm not going to test you on Riemann sums. There is no point in the test where you'll need to write this notationally. This will not appear on the test, either in the problem or in your written solutions. You will not have anything like a summation. You will not be asked to approximate the area by doing a Riemann sum. Because I think it's silly when we have a far better technique. Okay, and so let's use our better technique. So let's try some examples. Suppose I ask you the integral from 0 up to pi 4, so we're going to do definite integrals, because the fundamental theorem of calculus here deals with definite integrals, so I have to do a definite integral. The integral from 0 to pi 4 of sine x over 1 minus sine squared x dx. Now, the reason I want to do this is I just want to get some practice doing these kinds of derivatives. These kinds of integrals. Now, what do? Well, we basically say, look, the only thing we know how to do is to take antiderivatives and evaluate. And in particular, I come back to this board right here. And I say, as long as I can make it look like one of these things, x to the power, sine, or cosine, or secant squared, or secant tangent, or 1 over 1 plus x squared, as long as it looks like one of those, I'm OK. I'm happy. So what I try to do is I try to say, OK, I'm going to try to make my integral look like one of those. Now, sometimes it doesn't start that way. So you have to work on it. You have to massage. You have to say, OK, you look a little rough. Let me just work out the kinks here. It's a lot like if you remember when we did limits way back at the beginning of the quarter. We'd have these really weird limits, and we say, well, I don't know what's happening. Let's work on rewriting them. And then if we rewrote them, we said, I see there's some simplification, and now I see what's going on. It's really the same thought process. So I wanted to think about how can I rewrite this integral so I can make it look like something up here. And once I make it look like something up here, I'm happy. So, any ideas? OK. So one of the techniques is to use identities. And this is a really useful tool. This is a good idea, say, on a test if you had something like this. So one identity that we have, so I'm still doing the integral. All I'm going to do is just rewrite this integral in a different way. And that's perfectly fine, as long as what's inside is the same. And one of the things we know is that 1 minus sine squared is cosine squared. That's legal. All I'm doing is just saying, let's rewrite the inside in a different way. All right, that's good. Now what can we do? So I look at this and I say, does this look like anything up here? Or can I make it look like anything up there? I'll give you a hint on this one. What's another way to write sine x over cosine squared x? Well, another way to write it is 1 times sine of x over cosine of x times cosine of x. Notice all I did was I just said cosine squared is the same as cosine times cosine. And as somebody pointed out, this part is secant. And this part is tangent. So it's good to know your trig identities. And in fact, a lot of the reasons that you learn trig identities, you don't realize it. Trig is incredibly useful for doing integration. It sounds crazy to say, but a lot of integrals that involve no trigonometry whatsoever, when you look at it, the best way to do them is to use trigonometry to figure it out. So that's why you work so hard to figure out all those identities way back when in trigonometry was, why did you have to learn these rules for reducing, combining sines and cosines, breaking them apart? It all comes down to trigonometry. It all comes down to integration. Once you see integration with it, you see, aha, that's why we bothered to learn all that. And now we're happy, because now we finally said, well, look, I didn't recognize this. I've never seen this before. But I have seen secant tangent before. So I've cracked the case. I know what an antiderivative of secant tangent is. It's simply secant of x. And now I need to evaluate this from 0 up to pi fourths. Which another way to say this is you take the secant of pi fourths and you subtract secant of 0. And then we have to remember what secant of pi fourths is. Does anybody remember? Secant of pi fourths? Root 2. Secant of 0? Rhymes with fun. It's the number 1. Good. All right. We're getting better at this. All right. There we go. So the integral from 0 to pi fourths of sine over 1 minus sine squared is square root of 2 minus 1. Okay. That one was easy. Suppose I ask the following question. So I guess, before we go to the next one, let's just, what's the moral of the story here? If you don't know how to integrate what you're given, work on it. How can you rewrite it? And we're going to learn some more techniques of how to rewrite integrals. In particular, next week we're going to learn the substitution rules. But essentially, you're not going to be given an integral you can't do unless there's something else going on. But usually you'll be given an integral that you can rewrite. So just practice rewriting. But it's not a new tool. It's the old tool just in a new setting. The old tool was when we did limits. We had to practice rewriting limits. Now we're just practicing rewriting integrals. It's the same idea. Rewrite until you get something you can do. Suppose I ask you the following question. I want to integrate from 0 up to 4 the absolute value of 4 minus x squared dx. Now, how can we do this one? Well, one way we could do this one, certainly, is we could say, well, what's the antiderivative of 4 minus x squared in the absolute value? Well, we really haven't learned the antiderivative of absolute value of stuff yet, so maybe that's not the best way. So here is another trick. How do we think of the absolute value of 4 minus x squared? Well, 4 minus x squared, if I were just to look at the graph y equals 4 minus x squared, it would look like this. What does the absolute value of 4 minus x squared do? Well, essentially it says anything that's negative, I turn positive. So the absolute value of 4 minus x squared looks like this. So it just turns these pieces that were negative to positive. Now, how do we go about doing this integral? Well, we're going to start at 0, and we're going to end up at 4. Now, it's easy to figure out where does it hit the x-axis. Well, when does 4 minus x squared equal 0? At 2, which is in between. So we're finding this area, and we're finding this area. So another thing that we can do is if we have an integral that we don't know how to do the whole thing, well, let's break it up. Let's think of it as two things. Let's think about what happens from 0 to 2, and let's think about what happens from 2 to 4. So I'm going to think about this as two separate pieces. They say breaking up is hard to do, but no, breaking up is easy to do. Because we have that basic rule that says, if you integrate from A to B and then you integrate from B to C, it's the same as integrating from A to C. So we can break it up into pieces. That's no problem. The reason we're doing it, though, is that we hope that by the time we're done, that it simplifies things. And in fact, what happens when I take the absolute value of 4 minus x squared and I'm between 0 and 2? What does it become? Does the absolute value do anything here? It doesn't do anything. So that this integral here is the same as the integral from 0 to 2 of just simply 4 minus x squared, no absolute value signs anymore. They're gone. Now they're just regular old run-of-the-mill parentheses. We like those. They don't bother us. Now what about 4 minus x squared if I'm between 2 and 4? What happens to those? Well, see, that was the part where originally I was going down, but now I flipped it and I'm going up. So between 2 and 4, absolute value actually does something, and it just changes the sign. So that this integral here, well, all I need to do is really say that this is the same as x squared minus 4. Essentially multiply the inside by negative, and then I can drop the absolute value. And so now we're happy. Why? Well, because we know a couple things about integrals. One of the things we know is that we can break them up over addition. So I can think of the integral of 4, the integral of x squared, and the integral of x squared, and the integral of 4. And these fall under this category here, where I have the integral of x to a power. So now I've made it look like something I can handle. So I come back here, and I say, OK, so this part will become what? Well, what's the antiderivative of 4? 4x. What's the antiderivative of x squared? 3x cubed. OK, so I find the antiderivative of the inside, and I'm going to evaluate this from 0 to 2. Plus, now I come to here. What's the antiderivative of x squared? Oh, we just said 3x cubed. And the antiderivative of 4, oh, we already said that. That was 4x. The only difference is we're just changing the sign. Again, I evaluate from 2 to 4. And now we start plugging things in. So we get 4 times 2 is 8. Minus a third times 2 cubed, that's 8/3. So that's plugged into subtract 0 minus 0. That's nice. I can handle that one. Plus a third times 4 cubed, which is 64. Minus 4 times 4 is 16. Minus a third times 2 cubed is 8. Minus 4 times 2 is 8. All right, so what happens? Well, if I look at it, I have a plus 8 here. And I also have, if I bring this in, I have another plus 8 here. And I have a minus 16. So when I put all those together, I get 0. The plus 8, and the minus 16 all cancel out. What's left? I have a minus 8/3, a minus 8/3. The zeros aren't important. And I have a 64/3. So this is, we have 64/3, minus 8/3, minus 8/3. But of course, we can just put the 64/3, minus 8/3, minus 8/3, put it all together. 64 minus 16, 48, divided by 3, which is 16. So the integral from 0 to 4, the absolute value of 4 minus x squared dx is 16. OK, so here are just 2 things that we can do with integrals. Some of them you may have to do on the final. All right, so let's jump ahead and do the fundamental theorem of calculus. Part 2, the return. All right. Now here, the first fundamental theorem of calculus said if I want to do a definite integral, I just need to use an antiderivative. So in some sense, they're saying doing this integral gives an antiderivative. So this fundamental theorem of calculus is not a big surprise. It's going to look at, well, what happens if I try to take the derivative of the integral? Fundamental theorem of calculus. Part 2. Same assumptions. So f of x is a continuous function on a less than or equal to x less than or equal to b. Then, if I take the derivative with respect to x of the integral, well, let me say c to x, f of t dt, this is equal to f of x. Now, let me just point out here, I put c here. C can be anything. Doesn't really matter. Anywhere where the function is continuous, and then you're looking at the definite integral, you can just pick any value you want. It's unimportant. You can say c equals a if you want. All right. Before we get into this, let's think about what this is saying. What does this measure, this integral c to x of f of t dt? Well, I can think of this as a function of x. One way to call it is a of x. Because how do we interpret f of t dt? The integral of f of t dt. Well, the way we've done it is we said, well, this, in some sense, is the area here. Now, I put area in quotation marks because we had this kind of weird thing where area could be positive or negative. And we grew up always thinking area is positive. That's why I have to put area in quotation marks. So that, in essence, here, what I'm saying is, what's the total area from c to x? Now, as I change x, I change the amount of area. So that the total area here does vary as I vary x. So this is some function which depends on x in just looking at how far over do I look to see what my area is so far. So I have a function of x, and I take the derivative of that. And this says that you just get what you start with. Which, in other words, if we think of this, this is an antiderivative of f of x. Is another way to say the theorem. So how do we prove it? Let's just step through the proofs. Well, this theorem is saying, well, if you take a derivative of something, you'll get this other thing out. So what do? We take the derivative. We know how to take the derivative of things. We're masters at that. So we're just going to start. We're going to say, well, let's look at the derivative of this thing. C to x, f of t dt. Now, even though this looks like a really weird function, it's just a function, we're not intimidated by the fact that it looks weird. We always do the exact same thing. It's a limit as h goes to 0, where what do? I take my function, and instead of x, I put an x plus h. So where is the only change? The only change is where the x is. The only place where x shows up is up here. So this is the integral from c to x plus h, f of t dt, minus the integral of c to x, f of t dt, divided by h. So remember the definition of derivative. You take f of x plus h, in this case this, minus f of x, in this case this, divided by h. So this is the limit as h goes to 0, 1 over h. I'll just pull the h in front. What can I do with these two integrals here? I can combine them. Because notice this goes from c to x plus h. This goes to c to x. So I can basically combine them into one integral. And where are the bounds going to go from? From x to x plus h. So this is using our fact that if we have two integrals, definite integrals, integrate from a to b, and then you integrate from b to c, it's the same as just doing the integral from a to c. That's this fact here, just written in kind of an unusual way. All right. So now what I want to do is I want to focus on this for just a minute. Once we understand this, then we'll be good. So let's come over here. Y equals f of x. I should make it more curvy. Let's say this is x. Let's say this is x plus h. And so what do I have? Well, I'm trying to figure out something about 1 over h, the integral from x to x plus h, f of t dt. So try to make that look like an f. So in other words, this area divided by h. Now, if you look closely, the reason I came back to here is I have this fact. If I have a function bounded below and above by some constants, then those same constants bound above and below the integral, 1 over b minus a, integral from a to b. Now think of x. Let's say this corresponds to our a. This corresponds to our b. Just for this theorem here. I should use probably a prime and b prime, but just think of it in terms of this theorem here. Then if you look at it, what happens? This says that 1 over b minus a, well, b minus a in this case is h. So this 1 over b minus a is exactly the same as this 1 over h. And then I integrate from x to x plus h, which is exactly the same as integrating from a to b. So in other words, what I can say is that if I can get a lower bound for f of x, say it's little m, and I can get an upper bound for f of x as big M, then this integral is going to be between big M and little m. Now I need to really say what big M and little m are here. So here's what we'll do. We'll just make it really simple on ourselves. We'll say, let's let m little h be the max of the function f for x, well, let's say between, not the max. Let me get this right. Little is the min, between x and x plus h. So whenever I look at my function between x and x plus h, I just say, here's the smallest value. I'm going to call that little m. Similarly, mh with a capital M is the max of f between, sorry, I'm writing very small. So the little m is the min, big M is the max. So in this case, big M turns out to be on the right. So little m is on the left, big M is on the right. It doesn't have to be in the right or the left. It can happen somewhere in the middle. You can have really erratic functions where it can happen, pretty much do almost anything you want. So the picture here is we have that this little mh certainly is a lower bound for this integral, and this big mh is certainly an upper bound for this integral. And now we say, well, what do we want to have happen? Well, what would be nice is if we knew what happened to little m of h and big M of h as h got smaller and smaller. Now, looking back at our theorem, what haven't we used yet? There's a word we haven't picked out yet. Here, let me underline it. There's a hint. Okay, what haven't we used yet? We haven't used continuous yet. Okay, what does it mean to be continuous? Well, it basically says that as you look at smaller and smaller intervals, your function isn't going crazy. As your h gets closer and closer, your function has to basically move less and less. So that as h goes to 0, what's going to happen is that these things are going to get closer and closer together. That's what happens with continuity. So as h goes to 0, we have that little mh and big mh both get closer and closer to a specific value. Now, what is that specific value going to be? Well, the specific value that it gets close to is essentially whatever the function is at x. So they get closer and closer to the function at x. That's the intuition. So in particular, here, and I apologize because I just wrote this, but I need to point out what happens here. As h goes to 0, this little mh, which is looking at what the interval from x plus h of f of x, it's going to get closer and closer to f of x. And it converges to f of x. And as h goes to 0, this big mh, which is the maximum between x and x plus h, also is going to get closer and closer to f of x, and it's going to converge to f of x. So here's the question. What happens to this middle thing here? It seems like we have something below and something above. It seems like we're squeezing something. I wonder if there's a theorem about that. Some theorem about squeezing things together. Do we have anything like that? Oh, yeah, we have the squeeze theorem, which says, well, look, if I have something below and I have something above, and they're both going to the same thing, then the something in the middle also has to go to the same thing. So in particular, that 1 over h integral from x to x plus h f of t dt, which is what we have here, as h goes to 0, that has to go to f of x. But we're done, because that's what we wanted to show. We wanted to show that the derivative of this thing was f of x. Okay. So it worked out. End of proof. Or as they used to say, quod erit demonstratum, which is a very fancy way of saying, okay, we're done. All right. Well, the basic idea is essentially from x to x plus h, f of x doesn't change very much. And in fact, as x is closer to x plus h, in other words, as h gets smaller, it doesn't change very much at all. Basically, just it looks like the value f of x in the whole interval. All right. That was easy. Now, if I look at these two theorems and I compare them, this theorem says if I first integrate, then I take a derivative, I get back to where I started. So it's kind of saying that derivatives and integrals are, in some sense, inverses of each other. Because we have that the derivative of the integral from c to x of f of t dt is f of x. That's fundamental theorem of calculus part 2. Let me ask you this question. So what if I reverse it? What if instead of taking derivative and then, instead of taking the integral then taking derivative, I take a derivative first? So first I take a derivative and then I integrate. What happens then? So when I integrate then take a derivative, I get back to where I started. If I take a derivative and integrate, do I still get back to where I started? Well, essentially, what we know is that the fundamental theorem of calculus, part 2, says that if I have this integral here, it's going to generate an antiderivative of what's inside of here. Now, what's an antiderivative of the derivative of f of t? Well, it's f of t. Now, here's the trick, though. This function doesn't return an arbitrary antiderivative. It returns a very specific antiderivative. So it returns an antiderivative f of x plus some constant. And the constant here is not arbitrary. How do you figure out what that constant is? Do we know anything about integrals in general? Any fun facts? Read my mind. Okay. What happens if I were to say x equals c for a second? What does this become? So if I look at specifically x equals c, this side here is, of course, 0. Because if I integrate from a to b and a equals b, there's no width. No width, no area. Now what about this side? Well, this side is f of c plus some constant. So where does the constant have to be? Well, if f of c plus the constant equals 0, then the constant is negative f of c. So just solve for c. So the moral is that certainly if you integrate, then take your derivative, you get back where you started. But if you take a derivative and then you integrate, you almost get back to where you started, but not quite. You're off by a constant. That's OK. We usually can take care of that. All right. Let's do some practice. Suppose I ask you the following question. What is the derivative of the integral from 1 to x of the square root of 1 plus t cubed dt? I should also point out really quickly here, although I haven't said it yet, the dummy variable inside this integral is not x. If I'm taking the derivative with respect to x, the x is in the bounds, not inside the function. So your dummy variable is something else, a different variable. But it doesn't matter what the variable is called. We call it t, but you can call it whatever you want. Theta sometimes shows up if you're doing trigonometric integrals. Y, it doesn't matter. OK, so this one, we shouldn't even have to think. This is one of those times we can just write the answer down. Because we have this fundamental theorem of calculus, which, of course, I've covered. How clever of me. Which says if I'm taking the derivative of some constant, doesn't matter what the constant is to x, of some function, very easy. It's just the function you were trying to integrate. And we're done. So this makes the problem nice. But now let's see if we can't make it more interesting. Suppose instead of integrating from 1 to x, for some reason I throw in 1 to x squared. Same thing, though, as before. Now what happens? We just square it. Well, we square something. We certainly squared the x up in the upper bound there. What's the relationship here? Well, what I have here is I have a function x squared. And that function x squared is inside this really bizarre looking function, which is this integral. So I have a function inside of a function. If you like, you could say that they're somehow chained together. Now, what rule do we have for taking derivatives of these kinds of things? The chain rule. Right. Don't be intimidated just because it looks really bizarre. It looks different than what we've done before, but it's the same basic idea. A function x squared inside this function, where before we just had x. So according to the chain rule, what do? Well, we would take the derivative of just this function, but let's pretend instead of x squared we had x. We would do that first. And then we plug in x squared. So in this case, I know what the derivative of this integral is. Normally it's square root of 1 plus x cubed. Well, I don't put that in. I put in square root of 1 plus the x squared cubed. Think of this here. If I were to spell this out, g of x is my x squared. F of x is this integral 1 to x square root 1 plus t cubed dt. So this is f prime of g of x. Do I need anything else? Am I missing something? Yeah, I'm missing the g prime of x. In this case, what is that? 2x. OK, so that's that derivative. So let's write down this nice general rule. So we have that, in general, the derivative of the integral from a constant, instead of saying x, we'll say any function of g of x of f of t dt. Now we just apply our chain rule. This is f of g of x times g prime of x. And it looks exactly like what we did before with the chain rule, except there's not a prime here, but that's because we are basically starting with an antiderivative of f as our outside function. Okay, that was easy. So let's spice it up. Suppose now, instead of going from 1 to x squared, that's not hard. Let's go from cosine of x to x squared. So now x shows up in 2 places. Now what do we do? Okay, so we can separate them. Now, because if we can get to the point where it's a constant to a function, it's like, we're already done. We just go with what we know. So what I do is I say, well, look, I know what I can do is I can integrate, say, from cosine of x, let's just pick a number, say 0, square root of 1 plus t cubed dt. Then I can integrate from 0 up to x squared, square root of 1 plus t cubed dt. All right. Well, okay, I can do that. Okay, that's good. Let's see if we can clean it up just a little bit. First off, I'm going to swap the order here. So this is the derivative of the integral 0 to x squared, square root of 1 plus t cubed dt. What's another way I can rewrite the integral from cosine x to 0? I'd like to have the cosine x on top, because that matches with this form here. So I'd like to somehow switch top and bottom. How do I do that? Yeah, I just put a negative sign. If you want to switch top and bottom, you throw a negative sign in there. So it'll be minus the integral 0 to cosine of x, square root of 1 plus t cubed dt. And now, what do? We just use the rules that we know. We've already done this derivative. So this derivative is the square root 1 plus x squared cubed times 2x, where I took the derivative of the derivative of the outside is square root of 1 plus t cubed. I plug in x squared in for t. Then I times by derivative of x squared, which is 2x. Minus, what's the derivative of this function? What's the derivative of this? I'll get you started. The square root of 1 plus cosine of x cubed. And the negative sign comes on the outside, on the end, because that's the derivative of cosine. So in fact, we have this thing. It doesn't matter whether we have it in the x in the top or bottom or both. And you can see that what's going to happen is, in general, if I have the integral from, say, h of x to g of x of f of t dt, I can do the exact same trick. I break it up. I switch bounds on the integral from h of x to whatever the constant is. And then I take a derivative using the rules up here. So this is f of g of x times g prime of x minus f of h of x times h prime of x. All right. So let's try a problem. Suppose I ask the following question. Suppose I say that capital F of x is the integral from negative 1 to sine of x square root 1 minus t squared dt. And I say, what is the tangent line at x equals 0? This might be a kind of question that I might ask. So to find the tangent line at x equals 0, what do we need to find? In general, what do we need to find? Well, we need to find f of 0, and we need to find f prime of 0. Because once we know f of 0 and f prime of 0, then it's just really easy to write down the tangent line. We already have x equals 0. OK, so which one do we want to tackle first? F of 0? F prime of 0? How about f of 0? So f of 0, according to the rule, I take negative 1 up to sine of 0 of the square root of 1 minus t squared dt. Now, of course, sine of 0 is easy. It's just 0. But I look at that integral and I say, wait a second. That wasn't on my list. That is not one of the integrals that we saw before. So how are we going to find it? Well, notice we don't actually have to find the antiderivative of this function, because this is a definite integral. I'm just looking for a value. Maybe if I were to look at the picture here, I know what to do. The square root of 1 minus t squared is actually the top of a semicircle. It corresponds to the x squared plus y squared equals 1. It's the top half of that, with intercepts negative 1 and 1. And I'm looking for the area from negative 1 to 0. How much area is that? Well, the total area of a circle with radius 1 is pi r squared, so pi. But I only want a fourth of that, so this is pi fourths. OK, so that's f of 0. How about f prime of 0? Well, to figure out f prime of 0, I want to figure out what f prime of x is. So let's find f prime of x. F prime of x is square root 1 minus, and then the inside function I replaced by the sine x squared times by the derivative of sine, cosine, and then the bottom is a constant, so we don't need to worry about that. Now we're done. OK, so what is f prime of 0? We'll do it up here. Well, it's the square root of 1 minus sine of 0, 0, times cosine of 0. Cosine of 0, 1. So the f prime of 0 is 1. And so now we're ready to say that the tangent line, in general, remember the tangent line is y is equal to f of a plus f prime of a times x minus a. That's the general formula for a tangent line, so we just plug in what we know. In this case, a is 0. F of 0 is pi fourths. F prime of 0 is 1 times x minus 0 is x. So pi fourths plus x. OK. And we'll start up again next time. Don't forget to turn in your homework. And at 3 o'clock is the gold medal match. Woohoo!